So let me try to take some of the ideas that we talked about last time, the development of the idea of work, and kind of crystallize them into a problem-solving strategy. So along the way, I will remind you about certain things we talked about last time, and then also try to give you kind of a roadmap of how to approach this. So the first thing that you're going to do in your strategy is to identify your object of interest. You notice that this is your first step as well in the forced problem-solving strategy. That's no surprise because it's a big, wide world out there. You have to decide what you're interested in and what you're going to exclude. You basically have to take a bunch of objects and decide that's my object and everything else is the environment, right? So it can affect my object, but I don't care how my object affects my environment. Next step, you want to, of course, identify forces that act on it. So, same first two steps as the forced problem-solving strategy. Of course, you need to know something about how the environment is going to push and pull your object of interest. But here, instead of continuing on like the forced problem-solving strategy with steps 3 through 6, I'm going to take a complete left turn and do something very different. Here's what we do next. Instead of choosing axes, right, in preparation for working with vectors and components and SOHCAHTOAs and plus and minuses, blah, 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 we don't do any of that, okay? The whole point of this method is to kind of be a high-flying, easy method to use. We don't need to set axes, okay? So ideally, no axes, no components, don't have to deal with any of that stuff anymore. What we do now is we compute the work by each individual force. So the work done. Here's how we do it. You use the formula work equals F delta X cosine of theta. This formula is meant to be as easy as possible to just plug and chug. These are only sizes. So they're always positive. They're just how big those vectors are. They're not the vectors themselves. And then you don't have to worry if it's cosine or sine. In the equation, we did the SOHCAHTOA once, so we never have to do it again. The answer is always cosine. But it does require that you identify the angle in a certain prescribed manner. In fact, this big clunky subscript here is not just because I enjoy writing. It's to remind you that it's a very specific angle. It's the angle between the force and displacement vectors when they are placed tail to tail. Measure the shortest angle between them. The angle can range from 0 to 180. Possibilities again. If they make a smaller than 90-degree angle, the work will be plus. If they make a 90-degree angle exactly, the work will be 0. And if they make more than a 90-degree angle, the work will be negative. So the cosine term being plus 0 or minus will control the work being plus 0 or minus. And we understood as well that the work being plus 0 and minus, that's a number, it's not a vector. The plus and minus has something that's very different in its meaning. In fact, what we're going to do next is we're going to add these works together. And that will somehow account for the entire environmental influence on the object. Now, the work energy theorem tells us that the net work will tell us the change in kinetic energy of the object. Kinetic energy, just to remind you, is 1/2 mv squared. So this is 1/2 mv final squared minus 1/2 mv initial squared. So here is one way you can imagine what's going on. An object's kinetic energy is like a bank account. It's motion energy. When a work is positive, it makes a deposit. It adds to the kinetic energy. When a force points more with the displacement, it's more helping your motion, right? You can go faster. Or as we say, to be more sophisticated, we say that it adds motion energy. It adds kinetic energy. A positive work is an increase in kinetic energy. A negative work is a withdrawal. It's taking away the kinetic energy. So what you're doing when you're getting the net work is basically like balancing your energy checkbook. If you look at your bank statement, some works will be positive, just like some you'll get some deposits, right? Some works will be negative. Those will be withdrawals. There may be some transactions that are zero sum. So when you get a work as positive, it indicates that it's making a deposit on your kinetic energy. When work is negative, it indicates you're making a withdrawal. And what you're trying to do here when you're adding up all your works is you're trying to figure out, accounting for all the different forces, are they putting energy in or taking energy out? And then at the end of the day, at the end of the month, you have more or less money than you started with, right? Or in this case, kinetic energy, right? So the idea being that while this may be a list of numbers that you have to add together, while they may be plus, 0, or minus, it's definitely not vector addition. This is a scalar addition. It's adding up a string of numbers, right? You don't need to know how to do vector addition to balance your checkbook. To look at deposits and withdrawals, you don't have to now. So that's the meaning of what positive work is. It's adding kinetic energy. Negative work is taking it out. And what you're doing when you're getting the net work is just trying to figure out, did more come in than go out? Well, then you have an increase in kinetic energy. If more went out than came in, you have a decrease. Or maybe your account balance at the end of all those transactions was that nothing changed, right? Those are all possibilities. So what do you do here? Once you have that, you just solve for something. In this equation. So there's your work method problem-solving strategy. You're still accounting for all the forces that act on your object, but you're doing it in very different ways. You're going to say, do those forces either add kinetic energy, withdraw kinetic energy, or have no effect on the kinetic energy? And then whether or not you speed up or slow down will depend on if more things are adding kinetic energy, or I should say if there's more kinetic energy added than withdrawn. Okay? So I'm going to do an example on this. Are there any questions before I do that? Okay, so let's do an example. Here's my situation. I have a crate on a table. It's going to be 10 kilograms. And I'm going to pull on it. So I guess you say it starts from rest. And I'm going to pull on it like this. The pulling force has a magnitude of 50 newtons. Now, of course, one of the possibilities here is that that pulling force is not enough to get it moving, because static friction can cancel it. That's something that you should know how to check if you're given the static frictional coefficient. In fact, that was a big thing on homework 5 and exam 1. But just so we don't have to do all that old hat stuff, let's just assume that it moves. So assume that the pulling force can exceed the maximum value of static friction. So we are going to move. Let me say that the kinetic friction that it contends with afterwards, the kinetic friction coefficient is 0.3. And I'm going to ask, after 5 meters, I've been pulling it for 5 meters, how fast is it going? All right? So, let's start. Step 1, object of interest, obviously it's crate. Step 2, what are the forces acting on it? I'm given one, so that's nice, but how many more are there?
3 more.
3. What are they? Normal, gravity, and kinetic friction. So I'll go ahead and put those down. Gravity, normal force, and kinetic friction. All in their appropriate directions. Gravity is always down, normal force is always perpendicular away from the surface, so that happens to be up, and kinetic friction is always against you. So this is a problem that you definitely should be able to do with the old stuff. I don't mean to imply that you couldn't have done this before. I'm just taking it out for a spin with the new method. If you wanted to do it with the force method, what would you do? You'd probably set your axes, set them like this, right? I'm just going to briefly talk through it. I'm not going to write it out because this is old stuff. Do that not because that's what you always do, but because the acceleration is in the x direction, so it puts one of the axes along that. N and mg cancel, and then the net force in the forward direction will be Fp minus the kinetic frictional force, right? So that's your net force, set it equal to ma, get your acceleration. Now we're not asked for acceleration, of course we're asked for final speed, right? So you need the acceleration, v initial is 0, and displacement is 5 meters. So there's your 3 things, right? You need 3 things for the constant acceleration equations, right? Initial speed is given, the displacement is given, and you can find the acceleration. You can then find v final, right? So this is your classic 1-2 punch. You use Newton's second law, F net equals ma, to find the acceleration, and then you happen to notice that the net force is constant, the acceleration is constant. We can use constant acceleration equations, right? So that's just a little bit of talking through what you would do if it was in the force method. Let's try the new method. So I'm going to not set an x and y axis. The only thing I'm going to do to my diagram is just add in the displacement vector. I'm doing it in a different color because it's not a force, right? There are 4 forces that act on this thing, and the displacement vector I'm just adding because it's going to be very handy, because I'm going to need to find the angle that that force, or so that displacement makes with each of those forces. So let's go ahead and make a little chart here. For each force, I want to get the theta between that force and displacement, and ultimately compute the work. So we have the pulling force, we have gravity, normal force, and friction. Okay. we have to imagine placing the displacement vector tail to tail with each force in turn. Luckily, it's almost already drawn like that. What is the angle between the displacement and the pulling force? 0. So I know right away that that work is going to be positive because it makes less than a 90-degree angle, right? Less than 90 degrees, including 0 degrees, work is positive. This force is going to help me. It's going to add motion energy. Okay? It's more helping the motion, pulling in the same direction as the slide. It's going to make a deposit on the kinetic energy. This work is going to end up being plus. What's the angle between the gravitational force and the displacement? 90. So what's the work going to be? 0. This force does not help or hurt the motion. It actually acts perpendicularly. I'm not saying the force is 0. I'm saying that the force doesn't help you go faster or go slower. It actually acts at 90 degrees to the motion. What's the angle between the normal force and displacement? 90. Another work that's 0. Okay. What's the angle between the frictional force and displacement? 180. The biggest angle two vectors can make to each other. And that's more hurting the motion, right? It's going to be a negative work. It's going to take away kinetic energy. Now, I'll point out that there is none to take away initially. It has no kinetic energy at all to start with. Okay, so we'll come back to that in just a second. So let's go ahead and compute the amounts. Are there any questions before I continue and maybe clear a little space? Okay, so let's continue. Clear a little bit of this, at least the steps that we did already. So let's compute the work done by the pulling force. It's the size of the pulling force, size of the displacement, cosine of 0 degrees, which cosine of 0 is +1. So we go ahead and put in, we get that that force was 50 newtons in size, the displacement is 5 meters in size, times +1, and we get plus 250 newton meters, which we call a joule. So the pulling force is going to add 250 joules of kinetic energy to this object. So if we make a little box here, our kinetic energy, it's initially it's 0, because we're not moving, right? We have no motion energy to start with. So it's like your bank account has a balance of 0. We just found that someone made a deposit of 250 joules. So, if it was up to that force alone, you'd now have a balance of 250 joules. Of course, that's not the only transaction that happens here. So let's work out friction. So that'll be the size of the frictional force times the size of the displacement, cosine of 180. Cosine of 180 is -1. So there is where your negative comes from. You don't need to put it in yourself. It's actually all taken care of. The formula will provide its own sign. You just need to identify the angle correctly. So, the size of the frictional force wasn't handed to us. So this is where we have to go and borrow a cup of sugar from the forces method. This is why there's no way we could have done this first. There's a little bit of a chord still attached to the forces method. We have to borrow the fact, I'm going to put it like this, that the size of the kinetic friction force is mu k times normal force. Which, doesn't seem like a big deal, it's just a formula, so you can just borrow it, right? So that tells us that the frictional force is mu k times the normal force, but the normal force we weren't handed either. So this is where we've just gone over to the neighbor's house, the forces method house. We borrowed a cup of sugar, figured out how large the frictional force is. We're going to have to go over for a couple eggs. Okay? How big is the normal force? 98. What is it? 98 newtons, yes. mg, right? So there is no way you can get that except by realizing that the y forces here cancel, right? F net y must be 0, therefore n equals mg. So there are occasions where you do need to borrow a little bit from the forces method like that. It's going to be basics like this, but it's not like we've completely come up with something that's independent of the forces method. In fact, it requires a lot of knowledge about forces because, of course, the same forces that we had to consider before and do vector addition to find the net force, now those same forces get their individual works computed. Okay? So we do need to know about how big the forces are. So I go ahead and put in n equals mg. And what do I get? Well, I get mu k times mg times delta x times -1. And if you plug in all those, I think you should find that all of those are going to be minus 147. So, what do we have? You had 0 to start with. 0 kinetic energy, so there's nothing that you could take away from, right? Like if you make $0 a year, you don't owe any taxes, okay? I like to think of friction as the tax man, okay? So if another force puts in 250, then friction takes 147 away. So your overall balance is not going to be 250. It should be 103, right? Okay. So what am I doing there? I'm balancing my checkbook. I'm looking at all the deposits and withdrawals to get the net worth. So let's, this is step 4, what I'm doing. And let me clear off the idea of step 4 so I can actually do step 4. So my net worth consists of my pulling force, my frictional force, my gravity, and my normal. Those are, generally speaking, all of the different transactions, although of course I found out that 2 of these do not affect my kinetic energy balance in any way. They're what we call guiding forces. They don't make you go faster or slower. They simply exist to do other things. So if we add those up, we find a net gain of 103 joules. So I can cross off my initial balance of 0 joules and say I have 103 joules of kinetic energy. So what am I doing there? I'm saying that 103 joules is my gain. That's the difference between my final and initial. But of course, I know that I started with nothing, right? So if I start with nothing and have an overall gain of 103, what do I have? 103, right? So I can say that 1/2 mv final squared is 103 joules. And by the way, if at this stage you have the individual kinetic energies are always positive, right? You can have negative changes, that just means decreases, but if at this stage you had a negative on the right-hand side, you're going to have problems because you're going to try to square root it, okay? So remember that works can be negative, but kinetic energy can never be. So the analogy, again, this is not quite so true anymore because banks let you borrow after into the negative balance, okay? So let's say your bank doesn't let you do that, right? Your bank account balance is either 0 or more than 0. Any one transaction, of course, can be negative. That just simply means it's a withdrawal. But your overall balance can't go below 0, right? So even though we had 147 joules go out, you can't go to negative balance overall. Your kinetic energy can't go negative, even though a transaction, which is a work, can be negative, which means you're taking some out. So, question?
Yeah, this came into my mind. Wouldn't this be also a check for forces as well? Because if the angle of gravity is like 90 and normal gravity is going to be 0, wouldn't that be also a check as well? Like as a
So you're saying this angle is 90, and sorry, what was the other part?
and then the normal force is like 90.
Yep.
And that would be like a check right there for like the forces.
Well, so if you're at 90, you're not with or against the motion, so there's no transaction there, right? So those forces neither help the motion, they don't add energy to the motion, they don't hurt the motion, they don't take it away. Does that sort of make sense? I'm not quite following your question.
It's like what I'm referring to is like when you cancel the normal force and then the force of gravity cancels that out.
Right.
And since there's no normal force cancel out, there's no work added to it.
Right. Well, I mean, you're certainly correct that the nominal force and gravity cancel with each other. But even if you don't consider that, if you had just one of them, for instance, then even just one of them alone doesn't affect the kinetic energy. The fact that they both happen to not affect the kinetic energy because they're injuries to the motion is not really necessary for the two to cancel each other. For instance, if for some reason the normal force was bigger than the force of gravity, I guess that would be like the surface was rising or something, like you were pulling something along in an elevator, right? They still would do 0 work each, right? Actually, that would be a bad example because you would also be displacing upward. But sorry, I'm just trying to do this on the fly. But the point I'm trying to make is that you're right that they cancel with each other, but they already individually don't do any work before that. Does that sort of address your question? Okay, sorry, I didn't quite follow that. Yeah.
But if you manipulated the question where you had 147 going in and 250 coming out, so the work net would be negative 103 joules?
So you're saying if I reverse the signs on these guys?
Yeah.
That's correct. So if you had 250 joules going out and 147 coming in, you would have an overall loss. That would mean that your kinetic energy is decreasing, which means that you had to have something to draw from, right? The only way that you could have 250 coming out and only 147 going in is that it has to have a balance in there already, right? So what would that would actually represent is something that already is moving, and then the forces around it would be taking out more energy than putting in, so it would be slowing down. So the kinetic energy would be decreasing, but of course you can't decrease more than 0. So you would have to have something in there to start with. Does that make sense? Okay, and so here, just to complete the problem, we can solve for V final. And V final, if I've done this correctly, should come out to be 4.5 meters per second or so. And it's a good exercise to try it with the forces method, calculate the acceleration, and then use the constant acceleration equations. Make sure you can get that it's the same answer. Okay? So that's a little bit of how to do the work method. This is meant to be a fully worked out example. Rather than do another full example, I just kind of want to briefly sketch out another one. Are there any questions on this one before I kind of give a little sketch of another one? Okay, so let me just briefly sketch out another one. Let's do it on incline. Nice thing about an incline is that I don't need a separate pushing force to get the motion started. we learned that something can get started even on a friction incline on its own if the angle is steep enough. So we could, for instance, have normal force, gravity, and kinetic friction. And let's also throw in let me throw in an angle. Let me say the angle is 30 degrees. And I should also, let me draw in the displacement vector. So it's going to slide down, so that's the displacement. So let's do the same deal. I name the force, identify the appropriate theta that'll go into the work formula, and make predictions about the sign of the work. So we have the pulling, no, not the pulling force, just kidding. We have normal force, friction, and gravity. So to get the angle that goes in the work formula, you have to imagine each force in turn, tail to tail with the displacement. Let's start with the normal force. What's the angle between the normal force and displacement? 90. So what's the work? 0. Once again, the normal force does no work. It's like it's always perpendicular, no matter what we do. Well, that's going to be generally true, right? You can only move along a surface. You can't move into it. And the normal force is always then going to be perpendicular to you. So this helps us to kind of think about general laws that we can kind of say are true in different problems. So kind of let's write down some rules of thumb. We seem to have discovered a common thread that the work done by the normal force is 0. And it's because the normal force tends to be perpendicular to the motion. That's something you can count on. Now, it's not that the normal force can never do work. For instance, if you're lifting something in your hand, its displacement is upward, and the normal force is also upward. So then they're not 90 degrees. So notice that the hand itself has to be moving, right? So this is true when the surface itself is stationary. So as long as you don't have some crazy situation where the surface itself is moving, you can count on this. And by the way, we wouldn't normally call this a normal force. We tend to call forces like this pushing forces. So it's semantics for sure, but normal forces we call normal forces from a stationary surface that doesn't want to get smushed. And when it's a moving surface like your hand, we tend to call it a pushing force because your hand doesn't want to get smushed. That's completely just wording, okay? Okay, so that's one rule of thumb that we can count on. If we have a surface which is stationary, it cannot do any work because no matter what, the force that it exerts on you will be perpendicular to your motion. All right? Let's move on to friction. What is the angle between the frictional force and displacement? 180. Just like before. It's like it's always like that. And that is correct, because friction always acts against you. It was against you over here. It's against you over here. It'll definitely do negative work. It always takes away kinetic energy. Friction always tries to slow you down. If you don't slow down, it's because something added even more energy than friction took away. But friction always tries to slow you down. If we wanted to add a rule of thumb here for friction, for kinetic friction, well, it'd be the size of the force, size of the displacement times cosine of 180, which is always -1. So if you wanted, that would be like one thing that you could plug in straight away. You don't have to contemplate what the angle is. If you're talking friction, it's always 180. So just throw it right in, and that's what gives you your negative. Your negative work, which means that friction takes away kinetic energy. Okay? Let's take a look at the final one, gravity. What's the angle between the force of gravity and displacement?
60 degrees.
60 degrees, right? This angle is what we need. And hopefully you can see it's the complementary angle to 30, right? See that? Okay, so that's 60 degrees. So a couple things I want to point out. This huge clunky subscript, it takes a while to write, but this angle, otherwise students are tempted to stuff in the 30-degree angle that they see in the problem. But notice that 30 degrees did not go in anywhere. This was 90, 180, and 60. Okay? So remember, the angle that goes into the work formula is not necessarily the angle in the problem. Okay? This course isn't about just plugging and chugging. It's about thinking a little bit deeper than that. Okay? The angle that goes into the work formula is the angle between the force and displacement when they're placed tail to tail. Okay? None of these are 30 degrees, even though that's the tilt of the incline. So, is this work going to be plus 0 or minus? Plus. It's still more with you, right? Than against you. It's under 90 degrees. So, in this problem, gravity is going to add the energy, and friction is going to, once again, be the taxman and take some of it away. Okay? Gravity, so far, is the only one of the three that we have appeared in both problems that seems to have eluded some kind of trick. So we said that the normal force is always 90 degrees, the friction is always 180, but gravity over here was 90, and over here it was 60, right? So the next order of business is to think about, is there a shortcut for this? So one thing we can be sure of, gravity is nice in that it always points down no matter how you move, right? So in the first problem, we happen to be moving to the side, and gravity, which always acts down, happened to be perpendicular. So that's why the work was 0. In the second problem, we happen to be moving slightly downward, and so gravity, always being down, now is more with your motion, so the work will be positive. And of course, if we had slightly more upward motion, then gravity always points down. Now, it would happen to make more than a 90-degree angle with your motion. And then, of course, that's where gravity would start hurting the motion, right? When you go up, gravity hurts you. When you go down, gravity helps you. When you go to the side, gravity doesn't care. Does that make sense? So gravity is nice because it always pulls down no matter what you do. If you want to go with it, it'll help you. If you want to go against it, it'll hurt you. If you want to go perpendicular to it, just moving to the side, gravity doesn't care about that at all. It's not going to make you go faster or slower going to the side. We learned that all the way back when we were doing projectile motion, in fact, right? So, here we move, and this, by the way, is kind of like the, if you want to mark it down, this is kind of like the threshold we're crossing over from homework number 6 to homework 7 material. Okay? So the work method is something that I want you to try out at the end of your homework number 6. The work method can solve problems in and of its own right, but we're going to keep developing this method. I mentioned when I started the work energy unit that the work method is kind of like a intermediary stopping off point. It can do stuff. It'll get us warmed up to some of the ideas. You might question if it's better or anything like that. But we're going to continue the development. we're going to come up with something called the energy method, which is built off further ideas that we're going to get into right now. The energy method is so easy and so powerful that I think you'll become your favorite method. It's the main thrust of your homework number 7. But that is why it also takes a while to develop, and so I want to kind of do it in 2 pieces. I want you to try out the work method at the end of your current homework, and then I want to develop some further pieces so that we can really kind of get to the finish line and show you how it all works. Okay?